And this year, we are celebrating 70 years of being in India. We have been inspired every day of the last 70 years by scientists, policymakers, artists, students we've worked with across India. And this year, we want to share the stories of the great things we've done together, make new connections, tell new stories, and inspire millions of young people to develop connections for the next 70 years.
Today, we have this special lecture titled Landing on Comet by eminent scientist Professor Monica Grady.
Thank you very much, and thank you very much for inviting me to come here. Thank you to the JNP, and thank you to the A.B.A.A. for hosting me. And also, of course, thank you very much to the British Council for inviting me. It's a great honour and a pleasure to be here just to share some of the things that I like to talk about. And as you can see here, we have the comet that we landed on. And I tend to say, you know, we landed on. Or we did this and we did that, and by the end of the session you will think that I did it all by myself, single-handed, but I did very, very little of it. And I just want to say a little bit about where I'm from and my institution. So if you draw a line between London and Birmingham, which is the UK's second city, and a line between Cambridge and Oxford, where those lines cross is Milton Keynes. And we're a new city, only about 50 years old, and the Open University is a new university, again only about 50 years old. And here's a picture of our campus, and this is our building here, the Robert Hooke building, and where is it? There's the road there. Somewhere around about here is the dome of our telescope. So we have a small telescope on campus, optical telescope, and next to it, which you can't see, is an antenna for a radio telescope. The Open University, we do distance teaching, supported distance teaching, and our undergraduate students can access the telescope, the optical telescope and the radio telescope through the internet and be taught to use it through the internet. So there's some of the resources that we have. So anyway, this is my building, the Robert Hooke building. And it houses astronomers and physicists and planetary scientists. And what you can see in the front of the building, you can see that there are some landing lights there that look as if it's an airport. And at the Open University, when a new building is built, a small portion of money is put aside for public artwork. And the artist who created this was very taken by the idea that the scientists in this building were studying things from up there, aliens, all right? Things that came from out there to land on the ground, meteorites, bits of asteroids, and stars. And so he thought it would be a really good idea to invite those things to come down to Earth. So he built these landing lights so he could beckon the aliens down so they could come directly to our building, all right? I don't know how pleased we were at this idea. It hasn't been successful so far, but you know, you never know, something might come eventually. Okay, so I'm going to talk about a mission which went to a comet. And why would you want to go to a comet? What's the point of it? Well, part of the point is that comets, we know, have got a lot of ice in them and they've got a lot of carbon in them. And part of the rationale for going there is that when the Earth was first formed, it was incredibly hot and its surface was molten. And most of the original volatiles that were present in the Earth at the time were boiled away. But we know on Earth there's plenty of water here, there are plenty of organics. And so those must have come there from something else. And the something else was a mixture of comets and asteroids. And so one of the questions is to find out how much of the Earth's water came from comets. And another question is, what sort of organic compounds are there in comets? Because life must have got going somehow. The building blocks of life must have been brought to the planet somehow. and it could have been that they were brought by comets. Now, I'm not talking about something called panspermia. I'm not talking about bacteria being brought in by comets. I'm just talking about molecules being brought by comets. I should make clear at this point the difference between two sets of bodies that I've talked about already, and that's asteroids and comets. They've got a lot of things in common. They both sets of objects orbit the sun. They were both formed at around the same time, 4,567 million years ago, which is the age of the solar system. And when astronomers say, oh, the solar system's about 5 billion years old, or 4.5 billion years old, it's like they're being a bit slack, because cosmochemists can date fragments from meteorites, and they can date really precisely and really accurately that the solar system is 4,567 million years old. So it's a pretty good age number to remember, 4567. All right, so these objects, asteroids and comets, they're relatively unprocessed remnants from the protoplanetary disk. So when the sun first formed, this ball of gas and dust collapsing molecular fragment of a molecular cloud formed the sun, and around it was rotating a disk, a protoplanetary disk of dust and gas. Much of the gas went to form the sun, much of the gas then, the remaining gas, went to form the gas and ice giants, and then we have the rocky inner part of the solar system. And between the rocky inner part of the solar system and the ice and gas giants, we have the asteroid belt. And so asteroids, they orbit the sun. They're in fairly stable orbits between Mars and Jupiter. Their orbits are circular. They orbit in the plane of the ecliptic, the plane in which the Earth and all the planets orbit. And they are mainly made of rock and metal with some carbon. In contrast, comets are much further out from the sun. The Kuiper belt is out beyond Neptune, and we don't know how far out that is. We don't know how far out the Kuiper belt stretches. And within the Kuiper belt is an object called Pluto, all right? Now, Pluto used to be a planet. Are we happy that Pluto is no longer a planet? No. Who would like Pluto to be a planet? So a few people. Who would like Pluto to be a Kuiper belt object? Who doesn't care? All right, fair enough. But I will address this because it's something that occasionally the press gets exercised about. Oh, isn't it terrible that Pluto's no longer a planet? Well, you know, Pluto, it's very small, it's very dark, it's not very interesting, and it's so not interesting that it's the last planet to be explored by a space mission, the New Horizons mission, all right? Couldn't be bothered to go there beforehand, not interesting. We only went there because we've done all the others, all right? So you could say, not good as a planet. However, as a Kuiper belt object, it's so exciting and important that the very first mission to a Kuiper belt object chose to go to Pluto. So it is just so important, a Kuiper belt object. It's really, really important. And we found out some amazing things about this Kuiper belt object. So it's my opinion that Pluto made a really good career move in getting itself reclassified as a Kuiper belt object, all right? You know, and so it's like, but really, it doesn't matter. You know, it's an interesting object. It's dark, it's made of rock, it's got a lot of ice in it. We've got some amazing pictures from New Horizons. But it's not a comet. I mean, these Kuiper belt objects, they're in relatively stable orbits, but they are the source of many short period comets. The long period comets come from this thing called the Oort cloud, which none of us have ever seen. We don't know it's there or not, but it's hypothetical shell of comets where most of the comets come from. Now, what's interesting about the Oort cloud is it defines the edge, the gravitational edge of the solar system. And you can imagine that the planetary system next door, the star next door, also has an Oort cloud of comets, all right? And so by definition, you know, halfway between the two stars, you've got our Oort cloud and their Oort cloud. And you can imagine a sort of interaction between the Oort clouds, and occasionally, you know, because we're all in motion, you know, in our arm of the galaxy, you can imagine a perturbation and comets coming in to the inner solar system, and some of those comets might have been formed around the other star. And then, really excitingly, we had, a month or so ago, we had an interstellar object. We had that really long cylindrical thing that appeared out of nowhere, and we only found out about it when it was on its way out. It was on a trajectory like nothing else. You know, we didn't see it coming. We didn't predict it coming, and if it had come a bit closer and hit the Earth, you know, we might have been wiped out without knowing what has hit us. And so this interstellar object, it's been debated about whether it was a comet or whether it was an asteroid, or even whether it's a rocket stage from an interstellar alien spacecraft, because of its very long and almost cylindrical in shape. So it's just like, right, and it's known as, I think it's called ISO 1. The International Astronomical Union have labelled it ISO 1, Interstellar Object Number 1. You know, in the hope that there might be an interstellar object number 2, 3, 4, and 5. You know, but you never know when we're going to see them. Anyway, get back to comets. Right, so with these comets, they're on highly elliptical orbits. All right, so very steeply inclined to the ecliptic. They can be, some of them are almost in the ecliptic, but they can be very steeply inclined, and they can, you know, come up from behind and when you're not expecting them. And they're mainly made of dust and ice plus carbon. They haven't been differentiated. Some of the asteroids have got so hot when they were being formed, they differentiated into a core, a mantle, and a crust. That has never happened to the comets. They're primitive materials, and that's what makes them so exciting to study. They're primitive materials that are left over from the formation of the solar system. So there have been missions that went to comets before Rosetta, the one that I'm going to talk about, and the one that was studied most closely was Comet Halley in 1986, when it approached perihelion. And the first spacecraft to go close to Halley were Vega 1 and Vega 2, which were Russian spacecraft, which were on their way to Venus. And they passed between 8,000 and 9,000 kilometers from the comet. And they took this image. This is the first image of a comet. And you can see it's a bit fuzzy, but once you've applied, you know, a few sharpening techniques, you can see it's the classical potato shape of a cometary nucleus. What was more important, though, than getting this picture was actually the spectroscopy, the compositional information that came from Vega 1 and Vega 2. And they found, as expected, there was a lot of hydrogen and oxygen there because they thought it was made of ice. But there was also a lot of carbon and nitrogen, and also a lot of silicon as well. So the comet actually had a lot more non-ice material than had been expected. And when Giotto, which was the European Space Agency mission, when that arrived there a week or so later, its closest approach was 600 kilometers. And it took this close, you know, this is the best image that came. And the cameras on the spacecraft focused on this bit here. You know, the sun's over here. And this is one of a jet of material that is coming away. You know, the ice is subliming and dust is blowing off and forming the tail. And the cameras focused on this because they were expecting to be looking at a whitish coloured object. Because up until this stage, the main model of a comet was as a dirty snowball. All right, now at this stage, I am forced to ask, how many of you have ever made a snowball? Well, Hannah, you don't count, all right? So 2 of you have made snowballs. And have you made snowballs in India? Yes, some people have made snowballs, I know, in a leisure centre. I think you've got one here. You've got a sort of snow zone where you can go and make snowballs. But by and large, you don't have so much snow here. And, you know, it's supposed to be fun. You know, when it snows and you gather up the snow and you make a ball and then you throw it at your friends, all right? It's fun, all right? Trust me, it's not necessarily fun. But especially if you get some of the dirt in there, the soil, and it gets a bit grubby, and if you throw it, they can get hurt, you know. But the idea was that this is what a comet was like. It was a dirty snowball. It was mainly compacted snow, and it had got bits of dust mixed in it, and it might even have a rocky nucleus. The first images and the first analyses, though, of Halley showed that this image was wrong, that actually comets, this model was wrong. Comets were more like, they became known as dirty ice balls, or rather than dirty snowballs, they became known as icy dirt balls. So they were balls of rock which had some ice in them. And that model survived until Rosetta went to 67p, when it was found that actually there was the dust to ice ratio was much, much higher than we'd anticipated. Okay, so the British Council helps to spread British culture. So I shall do my bit as well to spread some British culture by talking about an artifact that was stolen under the noses of the French from the Egyptians by the British. That's how we define British culture, okay? So this is the Rosetta Stone, and I want to explain why the space mission was called Rosetta. Now, the Rosetta Stone has got on it a decree on behalf of King Ptolemy V, who, and it's dated around 196 BCE. And what's special about this stone, which is, you know, about this sort of high, and it was dug out of the Nile Valley in 1799, which was one of the few occasions that Britain was at war with the French, okay? And not only was Britain at war with the French, but Napoleon was a real, you know, I mean, Napoleon was a bit of a cultural hero. And he was absolutely concerned that the French archaeologists would bring back more Egyptian artifacts than those wretched English archaeologists who are out there digging up the Nile as well. But the British managed to get hold of the Rosetta Stone. And on it, it's got a decree in Greek. It's got a decree in Demotic script, which was the language that was used by the court. And both Greek and Demotic script could be read by scholars. And they said the same thing. It was this decree on behalf of King Ptolemy V. And the third layer has got the hieroglyphs, the pictograms that the Egyptians used, which at the time could not be read. And so the decree from King Ptolemy V said, if you worship me with as a god, I will allow you to keep all your sheep and cattle. All right, so I think that's a reasonable request from somebody who wanted to be a god. So the assumption was the hieroglyphics at the top was saying the same thing as these two languages, and so the Rosetta Stone enabled the translation of hieroglyphics. Now, that was important because at the time it was believed that the Nile Valley and the Egyptian culture, the pyramids and all the stuff that went with it was the start of humanity's education and cultural heritage. Now we know since then that that's wrong because there's been cultural heritage developing independently all over the world. But at the time, the Western world believed that cultural heritage, the dawn of the thinking mind came in Egypt. And so when scientists who like to believe they're cultured thought we're going to look for the name of a mission which wasn't just going to open up humanity's eyes to the dawn of its culture, but it was going to open up humanity's eyes to the dawn of the entire solar system and the understanding of our own origins. You know, they chose the name Rosetta, which is like, okay, well, why not? Let's go for something big. Now, the lander on the Rosetta spacecraft is called Feli. And Feli is also in the Nile Valley. Here is a town called Aswan, all right? And just to the south of Aswan is Feli. And Feli is a small island, and on the island of Feli is a temple, all right? And this temple was a real famous place of pilgrimage because it was dedicated to Isis, the mother of all the Egyptian gods. And guarding the gates of the temple was at least one obelisk, which was also borrowed by the British, and now it's in the grounds of a stately home in southwest England. And on this obelisk were also hieroglyphics and Greek writing. And the thought was that translation of the hieroglyphics on the obelisk helped in the translation of the Rosetta Stone. And so the same idea is that the instruments and the data on board the Feli lander will help and complement and help to interpret the data that comes from the Rosetta spacecraft. Okay, so that was the reason why we chose Feli. Okay, so that's enough culture for the time being. I have some more culture later on. I'm sure you can't wait. Right. So Rosetta, all right, was launched in 2004 to 67p Churyumov-Gerasimenko. But there was a big journey to get there, to start with. I mean, the starting gun was fired in 1990 when a working group met to plan for a joint European Space Agency NASA mission, and it was a Comet nuclear sample return mission. And this is what it was going to be, really, really difficult mission, very expensive mission. It was going to bring ice back from the comet. But 2 years later, NASA withdrew because it had a budget crisis. So what's new? So NASA withdrew. And ESA said, well, we'll go it alone, but we cannot afford to do the sample return. Instead of us bringing the sample back to you, you've got to send your kit, your instruments, up to the comet. It's like, okay, I'm sure we can do that, no problem. So it was accepted in November 1993 as one of the cornerstone missions, and it was going to go to Comet Virtanen, all right? So it was approved to go to this Comet Virtanen. My association with this mission is from being at the Open University, where we have a team which designed and built an instrument called Ptolemy, after King Ptolemy V, all right? And the instrument was built and it was delivered in March 2001 for integration. And I'll come back to all that in shortly. In March 2002, Rosetta, with Feli on board, was delivered to Arianespace, where it was integrated. And that takes place on the launch pad, almost, which is in French Guiana. So it all went over to French Guiana to be integrated onto the rocket, which was going to be launched in, I believe, December 2002. However, in November 2002, the Ariane 5, which was the first launch of a new heavy lifter, failed, all right? This was not the Rosetta launch, but it failed. Rosetta was going to be on the second one. So that meant there had to be an investigation and, blah, blah, blah. So the whole thing was postponed until March 2004. And, see the difference. We're no longer going to Virtanen. We're now going to Comet 67p. And the reason for that is because of the way that Rosetta was going to get to the comet. It wasn't going to go straight there. That would take far too much energy, far too much momentum required to get from the surface of the Earth. So what the spacecraft had to do was it had to do gravitational flybys. It had to do 4 gravitational flybys to pick up enough energy from the planets, gravitational energy, to get it out to where it was going. So it was launched in March 2004, it flew past the Earth, and then it flew past Mars, and then it flew past the Earth, and then it flew past the Earth, and then it was out on its way to... So we began March 2004. You know, if you follow this round, you get all the different trajectories for all the different flybys, all right? And so you get to a stage in June 2011 when actually Rosetta has done all the flybys. It's checked out all its instruments by making observations at asteroid Staines and asteroid Lutetia, and it's now on its way. What it's going to do is it's just going to go out into deep space, you know, hasn't got an engine, it's just going there with its momentum and its trajectory all nicely calculated by the flight dynamicists. And I like to think it was then switched off, all right, to save power, to save energy, to just let it go. And so it's drifting through space in the right direction, and I just like to think of it there, flying through space, silently, with just one little red light winking on the dashboard. None of this frantic hooting that goes on with some vehicles that I've travelled in. So it's there, it's on its way. And 2.5 years later, it's almost caught up with the comet. And so it's switched on in January 2014. Now I want you to think back to that slide where there was, how many years had we already gone? All right? We'd already gone, you know, let's say from here to here. So that's 11 years. You've already done 11 years. The OU people delivered Ptolemy in 2001. That's meant they started building it in 1999. All right, so you've already gone 11 years from here before launch, and now you've had another 10 years, the last 2.5 of which have been with no power to any of your instruments. And so your instruments have been in the deep cold, no power. So imagine taking your smartphone, the smartphone that you have today, and putting it in the deep freeze for 2.5 years, and then taking it out and switching it on. Do you think it would work? Do you think the battery would have gone flat? All right? Imagine doing that with a piece of technology that's 20 years old. All right? There were no mobile phones when these things were being built. There were mobile bricks, you know, with antennae about this that took a wheelbarrow to move around. It wasn't exactly, you know, very mobile, and certainly wasn't smart. And so the thought of doing this, you know, basically it worried everybody. Is this thing going to fire up? And so they switched it on. There was a big campaign, Wake Up Rosetta. Now, if I'd been ESA and I was really worried, I wouldn't have had the world's press focused on whether this is going to wake up or not. I'd have done it quietly the night before, just to make sure that it was actually going to work out. Now, I have no evidence that that's what ESA did, but, you know, it wouldn't surprise me. Anyway, so they switched it on, and not surprisingly, it didn't work. All right? So what did they do? They did what I did when I couldn't get my PowerPoint to load. I rebooted the computer, and so that's what they did. And so I gather that they had to reboot the computer 3 times. I don't know whether they had to do Windows updates or anything like that, but they rebooted the computer 3 times, whoops, and then Rosetta thankfully switched on. So what Rosetta then did was it flew towards the comet, all right? So it's flying to catch up with the comet, and it started to catch up and get close to the comet. Up until then, there'd been an assumption that comets were potato-shaped, or at a push, peanut-shaped, all right? Whatever they weren't this shape, which of course was interpreted as duck-shaped, all right? They certainly weren't duck-shaped. Now, have I got any engineers in this here room? Nobody's going to add, oh, we've got some engineers. Oh, good. I do like it when I'm talking to engineers because you're so easy to make fun of, right? So all the engineers said, oh, duck, or something very, very similar when they saw what shape it was. Because the engineers had spent, the flight dynamicists had spent some time making a shape model of the comet, you know, which from one side looked like a potato and from the other side looked like a peanut, all right? What it didn't look like was a rubber duck. And what they were concerned about was knowing the mass of the comet. Because if you're going to land something, you've got to know the gravitational attraction between the two bodies. When you've got something like this with two lobes, and you don't know whether the lobes are made of the same thing, how do you decide what the mass is? You know, by this stage, they've sort of got a fair idea of the density. Oh, let's call it very small. Let's call it 0.003-ish, you know, like every other comet that we've measured. But we don't know for sure. And we, you know, okay, we can measure this dimension and we can measure this dimension, but we don't know what's happening here in the neck. No, we can't land. It's too dangerous, far too dangerous. Now, the one thing I know about engineers is that they're very risk averse. They don't like to take chances. And to be fair, you know, that's all right. Because if you're going to build a bridge, you've got to be absolutely certain it's not going to fall down. If you're going to build a great big shopping complex, you've got to be absolutely certain it's not going to blow away, you know, in the next big hurricane. So you can't afford to take risks. And spaceflight engineers are even more risk averse than you know, civil engineers. I said, no, can't do it, can't land. It's like, but we've been 20 years, life's work. Can't do it, please. Well, the second thing I know about engineers is although they're very risk averse, they do like a challenge. And it's like, they're also, you know, like, no, you can't do it. Come back 10 minutes later. Actually, we've been thinking about it, and we found that if you do this, and you've changed that, and you fix that, then actually, we might be able to do it. So the engineers said, well, all right, you know, it's going to be very risky, but we do think, you know, we don't want you to waste your life's work. We think that, yes, you can land on this comet. However, there is a proviso. You can only land on this comet if it doesn't change its shape very much. And whatever happens, we've got to be able to see on the comet somewhere flat and smooth where it can land. It has not got to get more jagged in appearance. It's not got to get looking more irregular. Oh dear, it looks more irregular. All right, so by October, by the time caught up with the comet and taken lots and lots of images, by this time Rosetta has caught up with the comet and it has started to go round the comet. It's not in orbit round the comet because to be in orbit it has to be gravitationally bound, and it's too small to be gravitationally bound even by this small object. And so it's describing paths around the comet. And if you took the paths it was describing and stretched them all out, it would look like a bar of Toblerone because they were all sort of triangular. And so the engineers had another wobbly. You know, it's like, oh no, it's not safe, you can't land, you know, what's this happening here? You know, it's too difficult. But, you know, by this time they'd sort of decided that, well, you know, come what may, you know. Engineers go from risk averse to gung-ho very, very quickly. All right, that's the third thing I've found out about them. Once they've decided it can be done, then they're going to do it. All right, so here we have, you know, a really iconic view of the nucleus of Comet 67P. Here's another view of it up there. All right, now this is a view taken by the VLT in Chile, all right, one of the world's most powerful telescopes. And it does look like a comet. It's got a tail, it's got a nucleus, it's a very traditional sort of view of what a comet looks like. But when you're up close, you don't see that tail. You can't see the tail. Now, there are jets coming off from the comet, and if Rosetta got too close, then what happened, and it did this a couple of times as the comet got closer to the sun, what happens is if there's a sudden unexpected burst of dust coming off, then the star tracker gets confused. So the way that Rosetta was keeping station was to look at the pattern of the stars. And if you've got lots of dust there, then it's not, it doesn't recognize the pattern. And so it goes into safe mode. And so you've got to reboot it from safe mode, which is almost as good as trying to reboot it from not starting. All right? And so, although there was a tail, and you can see here's a picture of the tail. And you can see here's the nucleus of the comet. And here's the tail, which goes on for over 10 million kilometers. And this central nucleus is sort of 4 kilometers in its longest dimension, both height and width, all right? So you've got something 4 kilometers producing a tail of over 10 million kilometers. Now, I apologize, because I gave this talk in Trivandrum, and I meant to update it, and I forgot. So here is the comet and its shadow, all right? And this distance is the same distance from the Kerala State Science and Technology Museum to Trivandrum Airport, all right? So the comet would fit in 4 kilometers. So what's 4 kilometers away from here? Tell me something. Is there a railway station that's 4 kilometers from here, or the British Council? Oh, right, okay. So the comet would fit nicely between here and the British Council offices, which, given how many of you know where the British Council office is, it's probably not telling you very much. But anyway, so you've got what I'm saying is you've got a small object which will easily fit inside a part of a city, and it's producing this enormous long tail. But when you're up close to it, you can't actually see the tail. So we've now got up to about October. And it's time to start thinking of where Feli is going to land. And so ESA establishes a working group, and they produce 10 potential landing sites, and then they evaluate them, and it's going to go to landing site J, which is over here. It's the one landing site that isn't on the slide that ESA produced, but there you go. So it's on the front of the head of the comet. So once they decided they wanted a landing site, they had to get a name for the landing site. So they had a competition, and I won the competition. Yay! The landing site was called A.B.A.A. And this is the Rosetta and Feli teams award this certificate to Monica Grady to acknowledge your proposal of A.B.A.A. as the name of the landing site. All right? It's like brilliant. What I've very carefully covered with my picture of my certificate is the number of other competition winners who actually also chose the same name, which was quite a lot, all right? Quite a lot of hundreds of people. And that is where we come to some more culture. And this is why it was called A.B.A.A. and why it was a good name to call it. Remember, we have got Aswan here. Now, at the time the ancient Egyptians built Feli, there wasn't much at Aswan. But more modern Egyptians have built at Aswan a series of dams, which has changed the water level. And so the temple of Feli was getting eroded, getting flooded on a regular basis. And Feli, the temple, was a UNESCO World Cultural Heritage Site. So something had to be done about it. So UNESCO found an island just above the Aswan Dams called A.B.A.A. And they moved the Temple of Feli stone by stone, and they rebuilt it as a ruin on A.B.A.A. You know, you think since they were going to so much trouble, they could have at least, rebuilt it so it had a roof, but no, they decided to keep it as it was. So this actually is not a picture of the Temple of Isis on Feli. This is the Temple of Isis on A.B.A.A. So the island of A.B.A.A. became a safe haven for Feli. And so the landing site, Agilkir, was going to be a safe haven for the lander Feli, which is a beautiful story if only it had come true, all right? And it didn't come true. And so this brings me to the 12th of November 2014. So we've been going now since 1993, all right? So November 2014, 10 years, 10 and a half years since launch. And this is the last picture of the Feli lander taken by the Rosetta spacecraft. And it was important, this happened at 10 o'clock in the morning, and it was important because these legs had been folded up while Feli was on board Rosetta, and it was important to see this image to see that they had actually deployed, because on these legs their feet were screws, ice screws, which were going to screw into the surface of the comet and hold Feli steady. So this was the start of a really interesting day. And the day was in Darmstadt in Germany, which is where ESA's Science Operations Centre is. And so they'd invited lots of people there. They'd invited Ian Wright, who should have been talking tonight, because he is the principal investigator of the Ptolemy instrument. They'd invited me, not as Ian's wife, but as a science communicator and also as the principal science advisor to the Ptolemy team. They'd invited loads and loads of journalists, they'd invited politicians, you know, the mayor of the state was there, the science ministers of all the different ESA countries, they were all there, you know, all the great and famous. And so they put us in this room and we watched this go at 10 o'clock in the morning. Fantastic. Now, I don't know if you remember, in 2013, the Curiosity rover landed on Mars. And I don't know whether you remember NASA's great PR video that they produced. It was called 7 Minutes of Terror, all right? Because Curiosity or its host was going to come through the atmosphere of Mars, and for 7 minutes, NASA headquarters or NASA science operations were not going to know if it had survived its passage through the atmosphere, had it, you know, burnt up, because Mars, you know, eats things, all right? It didn't eat Mangalyaan, which is fantastic, but it eats lots and lots of things. And so they had this amazing video called 7 Minutes of Terror, which was all stirring music and yet really got you going. Well, ESA likes to think whatever NASA can do, it can do better, all right? It can do more of, it can do better, as if. And so what we had after this, we had 7 hours of boredom. Because the next thing was not going to happen for another 7 hours, all right? It's like, right, it's gone, we've got to wait 7 hours, and then it's going to land. It's like, right, so you've got 200 people, including lots of journalists, in this room in Darmstadt, out of the city centre of Darmstadt. Nothing to do, a few sandwiches to eat, ESA coffee to drink. My God, ESA's coffee, it's the same recipe that they use to fuel the rockets. It's disgusting. You know, the best you can say about it is it's a brown liquid. You know, it's just awful. Got an enormous amount of caffeine in it, though. So by the time, you know, sort of 3 o'clock in the afternoon comes round, you're absolutely wired by all this coffee you've been drinking. And the sort of the tension and the hyperactivity in the room. Really amazing. And so it was about 3:45, 4 o'clock, where we got this image. And this is the first image of the landing site from Feli, and you can see here is one of its legs. And so this is the picture of Comet 67P, and everything seems to be, you know, all systems go. It's like, right, here it is. And there's nothing we can do about it at this stage. It's there, it's either going to land or it's not going to land. But we have great faith in our planetary flight dynamicists. They know it's going to land. And they know what time it's going to land. And they know what time we will get the signal back. All right, so they know it's going to land around about 4:45, and they know we'll get the signal back at 5:02. Okay? Right, now are there any journalists in the room? All right, nobody's going to admit to being a journalist. Journalists are even more fun to make fun of than engineers, all right? Because journalists, by and large, don't understand planetary dynamics. You know, for some strange reason, they've missed it out of their learning. And so they don't understand when somebody says, well, yes, it's using gravity, and that's the main force. And no, you can't make it work any faster. And if the people who know these things say it's going to land at 4:45, then yes, it's going to land at 4:45. It's not going to land at 3:45 or 4:15. So we've got about 3/4 of an hour to wait. And by this time, Ian and his colleagues, the other principal investigators, have left the room. They've gone to another smaller room because, for reasons best known to itself, ESA had the principal investigators of the 11 instruments at Darmstadt, but it had the rest of the scientific teams in Cologne, which is a couple of 100 kilometres away. Why? Nobody really knew. So Ian's team was away from where he was. And so all the principal investigators went off into another room so that they could talk to their teams to make sure that everything was ready, because there were pre-landing experiments that were going on. And so the journalists hadn't anybody else to badger, other than that. They couldn't badger the important people because they were over there. And they were sick and tired of interviewing each other. So they started interviewing the few random people who were left in the room, and I was one of them. And it was one of these things they kept saying, you know, they'd come up to you and say, are you excited? Are you worried? Is this the most exciting thing you've ever done? Are you really, really scared? Do you think it'll land? Do you think it'll crash? Are you excited? Are you scared? Is this the most important thing you've ever done? And, you know, when you've had several hours of that, then, you know, you can't be...
Years for this.
I've waited years. I'm just so excited. I'm gonna cry. I'm sorry. It's fantastic. It's fantastic. It's wonderful. It's really, really wonderful. Sorry.
You want to sit down now, don't you?
Sorry, now I'll try and be a professional scientist. This is an amazing moment for a European Space Agency history.
Emotion just came over you.
Oh, I'm so happy. It's just wonderful. It's just unbelievable. We've waited so long, and now it's happening.
That was me in my redhead head days. And the guy that I hugged was David Schuckman, who's the principal science correspondent for the BBC, all right? And now whenever I see David, he sort of sidles away from me in case I'm going to hug him in hysteria again. But following that performance, I went viral on BuzzFeed, which I think, you know, that's pretty magnificent, you know, for a lowly scientist. But it was tremendously exciting. It was just superbly exciting. I cannot get over to you how exciting it was. And that excitement lasted for me for a few minutes. And then Ian and the principal investigators came out to talk and do press conferences and things like that. And Ian came up to me and he put his arms around me, and I said all the things that the journalists said to me. Were you excited? Were you worried? Did you think it was going to crash? You know. And he put his face close to mine and he whispered in my ear, "Keep smiling, it's all gone wrong." And so it's like, right, okay, what do you mean it's all gone wrong? And what had happened was it had touched down. And we saw touchdown. Now, I was stressing about the time before, and if you're sharp-eyed, you'll see, hang on a minute, she was talking about 4:45. That's 4:45. This is because this is universal time, and we were on Central European time. Okay, so it touched down. It touched down a little bit ahead of when it should have touched down. And then it bounced. And we found out within about 10 minutes, you know, the word went round. You could hear this sort of whooshing and they know, they've gone sober, they've gone sober, they've gone sober. You could see it going through the room, this news that it had bounced. And is it going to touch down again? We don't know. And it wasn't until another 2 hours later that these results are from the magnetometer, that actually you could see it touched down again, and there was a third touchdown, so it bounced twice, okay? And so we didn't know. So from the length of time it took to come back down again, you can calculate how high it had bounced, and so it wasn't known. And so the teams out in Cologne, they knew straight away that something had gone wrong. So it's like, right, okay, so what had happened? What had gone wrong? Well, there were three things that were going to help Feli land on the comet. The first thing was, as it was pushed out from Rosetta, it was going to have it was going to fall, and then there was a thruster, a reverse thruster, which was going to start slowing it down. Now, we'd known by 10 o'clock in the morning that that was not working, because it hadn't checked out, all right? So, but the engineers, like I say, you know, they were very much, you know, going towards the no-go. And it's like, what do you mean no-go? This is the only chance we've got, you know. All right, okay, but we'll give it a whirl. So it was going, and the idea was that Feli would be slowed down, a harpoon would fire and anchor it to the surface of the comet, and then the legs, which were already out with these ice screws, would hold it in place. For some reason, the harpoon didn't fire. It didn't fire. Don't know why. Didn't fire, so it bounced. And when it bounced, it was tumbling and twisting, and it landed on its side. And it landed on its side, bounced here, 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 landed on its side. It's only, you know, 1/2 kilometre, something like that, away from where it should have been, which is here. So that's why it landed early, because instead of landing here, it landed there. So it bounced, landed on its side here, somewhere dark. And what that meant was that the solar panels would not charge up. And so we only got 70 hours battery life from Feli. So it had a main battery on board, which lasted for 70 hours, and Ian is very pleased to show the picture of the voltage draining from the battery, and he'd got plenty of data, but he was allowed a last gasp, and you can see when he switched his mass spec on, and he drained the battery, all right? So Ian killed Feli, all right? So anyway, so they got some fantastic data. 80% of the data were acquired. The main data that weren't got was stuff that relied on the drill. So there was a drill that would come down from the bottom of the lander, and it was going to drill rock and ice. And then there was a distribution system, and Ian's instrument had ovens on it, which was going to do some experiments on the solid. Now, they did get some solid, and I'll tell you what they got in a tick. I'll just change the subject a bit, all right? So this is the prototype of the Ptolemy instrument that Ian was building. And this is Sasha standing up, and he's 6 feet tall. And if you can see this is welded angle iron, and these are all air-actuated valves. There's a lot of, you know, wires. There's a lot of pumps. There's all sorts of stuff. There's vacuum flasks. What you can't see off here is So this is Ian's first diagram of the system. And this is dated March 1994, okay? And so here we have our bulk sample. It's going to be heated. We're going to do this. We're going to purify the gas through a GC. We're going to do this. 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 Now, this is in the days before PowerPoint, all right, when you had to use a pencil and a piece of paper. And so this is Ian's, Ian's first diagram. And so here we are, 20 and a half years later, actually getting some data. So they built the system. They didn't build it for 2.7 kilograms. They actually got it down to 4 kilograms, which is not bad. This is the detector that they used. It's an ion trap mass spectrometer. And gas comes in here and it gets ionized. Now, the instruments that I saw this morning, some of them use a hot filament, hot wire filament. Some of them might use solutions, evaporated solutions as a filament. But what we're using here is nanotips, all right? And so remember, this was being built in 1999, when nanotechnology, was in its infancy. So they used these tiny little nanotips to actually generate electrons to ionize the gas. And then what happens is the ions go one by one, are released one by one as you change the voltage on the ion trap. So this is the ion trap mass spectrometer, and it counts the ions one by one. And it's about that big. So on Earth, we say that on Earth, God, in England, in Britain, that's the size of a cotton reel. Okay, if you're using cotton for sewing, that's the size of a cotton reel. And this is the Ptolemy instrument. This is the flight model, and you can see a hand there for scale. These two tanks are for helium gas, because the way one of the modes of analysis was to use a GC column. Now, for those who don't know GC, you've got a really, really, really long, thin pipe that's round up, and it's got a material in it that looks a bit like sugar. And what happens is the mixture of molecules goes through this column, and the light ones can get through faster than the big heavy ones that have to fight their way through. So you separate out the different molecules by using a GC column. And so what you've got here, this black box at the back, that's got all the electronics in. We've got a couple of ovens. We've got the detector down here, the ion trap down here. And this is to the outside world, okay? And so this whole lot weighs 4 kilograms. And believe me, if you're living with somebody who is building an instrument, a spaceflight instrument, they are really boring about how much wire weighs. It's like, oh, we managed to shave another, 200 milligrams off the weight of the wire. It's like, yippee-roos, all right? So you have to be very, very careful. And this is Ptolemy being integrated. And so this is the two base plates, there's one here and one coming out, of the Feli lander. Now, this is a mass spectrometer system, so it doesn't need to see anything. All it needs to be able to do is get to the outside world, all right? So it can go on the base plate. It can go, oh, we can put it in first. It can go in the middle, all right? And so if you're going to build spaceflight instruments, don't ever be building a mass spectrometer, because you will have to deliver first. And as I said, there were 11 instruments, so the 10 other principal investigators would sort of wait to hear from Ian. And if Ian was saying things like, well, I'm afraid we're a bit behind schedule. Oops. If Ian would say, oh, I'm afraid we're a bit behind schedule, they'd all go, that's terrible, you're letting us all down. Phew. Because then they never had to say how behind schedule they were. All right, so it's like, right, okay, so he was integrated first into this, and then it went off to be integrated onto Rosetta, and then Rosetta went off to be integrated on Ariane, and then it had to wait there for another year before anything could happen. All right. Okay, so this is the schedule of what happened. Here we have the bouncing again. And if you remember what time the signal came back, it was at 1543. And here, Ian's operation was in operation at 1543. Okay, here's 1543. Here's Feli. It's bounced and is tumbling. and Ian got 6 mass spec. All right? So he got six mass spectra as the comet, as the Feli was tumbling and bouncing. And so this is an instrument which is really delicate, really fragile, but it's got to be robust enough to actually stand the rocket launch, but you know, it's all padded round and braced for that. But here it is, it's on something which is bouncing and banging and rattling around, and it's still producing data. And here are some of the data which were acquired. So there were 2 sets of wavelength ranges, mass ranges that were detected. So we've got mass to charge down here. We've got here the water, which is by you know, far the most abundant species, and here we've also got carbon dioxide, which is the second most abundant species. So that straight away verified that the comet had got ice on it, water and carbon dioxide ice, which, you know, was not a huge surprise. So adding the 2 spectra together and then removing the water and the CO2 so you can actually see the detail of the other species, you can see they come in clumps. Okay, so there's lots of different interpretations, because what happens when you've got big organic species, they fragment into smaller species. So you've got to look at the combination of masses. And Ian came to the conclusion, well, I can't say Ian and his team came to the conclusion that this was from something that had also been observed on Halley's Comet, and it's called polyoxymethylene. All right, so poly is a polymer, it's lots and lots of things, oxymethylenes, all bonded together. And what's actually happened is you're fragmenting this polymer at different bonds. And the precursor of polyoxymethylene is formaldehyde. And if you build formaldehyde up in one way, you get this. If you build it up in another way, you get ribose, okay, which is a sugar which is very important in the formation of ribonucleic acid. So for Ian, what Ian and the team had been hoping for was to find some nitrogen-containing molecules, because they were hoping to find glycine. And they didn't find glycine. They found ammonia, and they found other nitrogen-containing molecules, but they also found this sugar, which had not been predicted at all, you know, because the results from Halley hadn't necessarily been accepted. Okay, so this next slide is a physicist's view of what chemistry is, okay? So chemists, especially organic chemists, I've got any organic chemists in the room? Anybody who will admit in public to being an organic chemist? Well, I was once. You know, carbon forms all these chains, and they're straight chains, or they're branch chains, or they're a network of stuff. And actually what happens is there's an enormous great naming system for organic chemicals, all right? Now, physicists who think, or especially astronomers, who think anything heavier than hydrogen is a metal, you know, they just can't cope with organic chemistry. And so the physicists who built the Rosetta mass spec, they produced this beautiful thing. And for ages, I thought this was either Africa or India. But actually, of course, it's the comet with its 2 lobes. And they found lots and lots of different molecules because they were analysing the gas. This was a sample that was on the Rosetta spacecraft itself, so it was constantly analysing the gas. And so what you've got here is you've got long carbon chains, long chains. Oh, let's put them in a group called giraffe, because it's got a long neck. All right, here are the nasty poisonous ones. Let's call them snakes, because these are poisonous. Acetylene, formaldehyde, things like this. Stinky ones, smelly ones, let's put them as a skunk. Sulfur dioxide, sulfur monoxide, hydrogen sulfide. Salty ones, hydrogen chloride. You know, all these sorts of things. Volatile, butterfly, nitrogen, oxygen. And then the king of the zoo, glycine. All right, they found glycine, they found the amino acid, which was really great. All right, so Rosetta followed the comet through perihelion and out again. And during that time, it was able to observe changes in the cometary landscape. Now, we're used to interpreting changes on the Earth and even on Mars in terms of terrestrial processes, rivers, glaciers, wind, things like that. You haven't got any of that on a comet. You haven't got gravity. You can't even say this is a hill and that boulder's rolled down the hill, because the thing is not only rotating on an axis, it's also tumbling as well. And so you've got, there's no way that's always up, okay? So there's a new sort of subfield being developed of cometary. I don't suppose you can't really call it cometary geomorphology, can you? But anyway, trying to interpret cometary landforms, because all you've got ice subliming, freeing dust, and dust settling back down again, falling back down again. So you've got, in effect, airfall. So that's been going on. Right. Feli was found a couple of weeks before the mission came to an end. And naturally, Feli was found right on the edge of the frame, all right? It'd be far too much to hope it was going to be right in the middle of the frame, wouldn't it? So it was found on the edge of the frame, this red box, and you can see it here. You can see its legs deployed and everything. So Feli was found, which was really great. What was decided was that Rosetta was going to make a landing. It was going to glide smoothly onto the surface of the comet. And so it was going to take a series of photographs, the last photographs, and they were sent back to Earth. So this is a series of the last pictures that Rosetta took, okay? As you're getting closer, you're getting into the most fantastic detail. Just look at that. Look at this. It's a scree slope. It's not a scree slope, but I do have a colleague in France who's got a PhD student who's got to count all those boulders and measure them. What a PhD, eh? What a nasty person. So, so they're doing that. And we're getting there, we're getting closer, and we're getting closer. And it's like that was thought to be the last picture. And look, it's out of focus. You can't trust these camera people. They can't even focus properly. So this was thought to be the last picture. And then a year later, they found another one, still in the can, as it were, which is much sharper. So this is a meter across with a resolution of 2 millimeters per pixel. And so that is the last picture that came from Rosetta. And so that was the end of the mission.
Rosetta had spent over 2 years at Comet 67P Churyumov-Gerasimenko, but her time there was already coming to an end. She had made millions of measurements and by now knew the comet inside out. She had taken photos from all angles, collected dust grains, and sampled the gases in the comet's atmosphere, especially water vapor, which was not quite the same as water on Earth. She had measured the gravity of the comet, the magnetic field in its surroundings, and how the comet interacts with the solar wind. During the 2 years, Rosetta had monitored how the comet changed as they moved closer to the sun and then away again. With all this information, scientists back home had learned many things about how comets formed and evolved. They also established that comets were made of the dusty and icy material left over after the planets were formed, and so they contain some of the oldest and best preserved material from the birth of our solar system. Rosetta had made even more remarkable discoveries. She found ingredients that were crucial for the origin of life on Earth. Perhaps comets had helped seed the Earth with these important ingredients when our planet was still very young. Scientists would definitely be busy analyzing Rosetta's findings for decades. Her mission had been a huge success. After a long search, she had even managed to find the strange place where Feli had ended up, fast asleep in a dark corner of the comet. But now, once again far from the sun, Rosetta was not generating as much power, and soon would not have enough to carry out her investigations. She could go back to sleep right away, but instead decided to undertake one last ambitious challenge. She was going to follow in Feli's footsteps and land on the comet. Rosetta was tired after 12.5 years traveling through space, but she was very excited about her last tasks. She would finally see up close some of the amazing sights she'd been observing from a distance for the past 2 years. And she'd get to sample the comet's gases closer than she had ever dared to go before. It would not be easy, but the experts back home had everything figured out and the date was set. Rosetta would be targeting a really interesting place on the head of the comet. She wasn't going to be able to talk to Earth ever again once she was on the comet's surface. After all, she was never designed to land. So she would have to send back her last images and data as quickly as possible before saying her final goodbyes. Even though her incredible journey was nearly complete, she knew that just like the other comet explorers that had gone before her, the legacy of her amazing mission would live on forever. She felt lucky to have had so many friends and hoped they would still think about her and Feli from time to time. Finally, after 786 days at the comet, the last day of her extraordinary adventure had arrived. Finally, Rosetta's big day had come. It was time for her to join Feli on Comet 67P Churyumov-Gerasimenko. And so ends the amazing adventure of our two extraordinary explorers, Rosetta and Feli, at Comet 67P. Farewell, dear friends.
And it was very emotional. I mean, if you've been working on something for 20, 25 years, it has taken up your entire scientific lifetime. Now, it's not that Ian and his team built the instrument, and then sat around for 10 years waiting for it to arrive. They're doing other things. So currently they're building a mass spectrometer to go to the moon in association with Roscosmos, and they're building one to go to Mars with on ExoMars. So so these things keep going on. But it was a great journey. It was a great, just a great experience. And it's true, the data that we have are still, all something like 123 kilobytes of it, something like that, which is what it was, are still being poured over by the team, by myself. And keep posted. Thank you very much.
How much of the water on Earth comes from cometary impacts?
Yeah.
So in what way has our understanding of that, like in what way have we understood that better after Rosetta went to the comet?
Okay, yeah, good question. Ian's instrument was hoping to do, and also another instrument which was on board, was to look at the deuterium to hydrogen and the oxygen 16 to 17 and 18 ratios of the ice. But they couldn't do that, neither of them could do that because of the failure of the drill. However, Rosina has managed to make some measurements of the DH ratio of the water. And what they've found is if you assume that the DH ratio of the Sun and of Jupiter, is the DH ratio of the protosolar nebula, and we know what the DH ratio is on Earth. We've got to look for the other end member to decide what the proportion is. And so there is a delta D value for the comet, which shows that the isotopic composition of the water is not the same as the isotopic composition of the Earth. However, it's very difficult to actually mix that isotopic composition with that of Jupiter or with that of the Sun to get the water on the Earth. And so we haven't answered the question, which is marvellous, because it actually means we've got to have another mission. But that's not so good, because it's going to take years and years and years before we can plan one. So it shows that it's not an easy answer. It's not something that dropped out of all the calculations straight away. We do know there is a proportion of water on a comet. The problem is that Rosina was not measuring the ice. Okay, it was measuring the gas, and you don't know what reactions had been going on as the ice was subliming. And so it's not measured absolutely the isotopic composition of the comet. It's measured the isotopic composition of the comet's tail, which is not necessarily the same as the ice on the nucleus. It's probably not going to be enormously different, but it's still something which leaves a lot of questions open.
On Earth, we find ice 1H, but on Rosetta, what type of ice do we find? Like, did you guys get a time to analyze what type of ice was? It was amorphous, or what type of ice classification?
That wasn't measured. One of those instruments wasn't taken up. I mean, they're looking at, as I just said, the instruments on Rosetta were looking at gas phase, and the instruments on Feli didn't get the ice to analyse because the drill didn't work. And anyway, none of the instruments were designed. So none of the instruments were designed to look at the structure of the ice. None of the instruments were designed to look at the optical chirality of the organic molecules. And because you've got to have a limit to the amount of instruments that you can take.
Some assumptions about the composition of the ice there, like it's super ionic or it's ice something.
We know there's ice there. A lot of it is carbon dioxide ice. And it's mixtures of carbon dioxide and water ice. And one of the things I wanted to know was what was the proportion of carbon dioxide ice to water ice. And then the sort of next level would be what's the structure of the ice. Now, the temperature at which this comet is spending most of its time. And so that, you can say, right, okay, we know what ice forms are stable at that temperature. But then again, are they stable at that temperature under extraordinarily low pressure? And also under cosmic radiation. So it's one of those things that, no, we don't know the answer.
I think I saw the distance of the comet from Sun as well as from Earth, right? So what was the distance of the spacecraft from the comet? While it was recording the images?
When it was doing maneuvers to try and decide where Feli was going to land, it was far enough away from the Sun that it could get closer to the comet. So the closest distance it got was 7 kilometers. All right, so it did some flybys at 7 kilometers. Most of the time, it was about 30 kilometers away. Okay. And it's one of those things. Before Feli landed, it was, some call it a debate, some call it an argument between the principal investigators of the Feli instruments, who wanted Rosetta to get as close as possible so you could get really detailed views of what the landing site was going to be, and the scientists on the Rosetta instruments, who wanted to get a more sort of holistic view of the whole of the comet, so they wanted to be further away. Yes. So it was about 30 kilometers, but occasionally, if there was a burst of a sudden jet, it would retreat. At one stage, it went about 1,000 kilometres away, and it was hoped it would get to the sort of magnetopause when it would be able to look and see, here's the end of the bow shock, but it didn't get there, and so the bow shock was even further away than that. And of course, as Rosetta got closer and closer to the sun, as it was going towards perihelion, it had to get further and further away because the comet was getting more and more
that was
active.
another question I had. So was it under the influence sun's gravity more or the comet's gravity?
Rosetta had thrusters on it and fuel, so it could be programmed from Earth to actually change its direction.
Okay.
And so that was what was controlling where Rosetta was when it was switched back on again.
Thank you.
We knew that the Philae thrusters were not working before it was landed, right?
Mm-hmm.
So we could have made sure that Rosetta would be brought as close as possible to the comet, and then made sure the Philae was landed so that it could avoid that tumbling, and we could have made Philae work.
If Rosetta got too close, all right, Philae would not be coming in at the right angle. All things have to be carefully calculated, and it's always a trade-off. You know, it's a trade-off between this and it's a trade-off between that. It's a trade-off between velocity and momentum and time, and it's a trade-off between this and that. And they, even with the thruster working or the thruster not working, they couldn't have got much closer than they wanted to. I can't remember what the distance was. I can't remember what it was anyway. But they couldn't. They couldn't have done anything on that time frame. They only found out the night before that the thruster on the top of Philae wasn't working, and that was too late to do anything about it, because they couldn't change anything, because they couldn't program Philae. All right, they couldn't change any of the programs on Philae and still have the opportunity to land when and where they wanted to.
One is about the magnetic property about comets. So you told in the video, it was mentioned that there was some study done on the magnetic property.
Mm-hmm.
So if you could give us some insights on it.
It's not an indigenous magnetic field, all right, like the Earth has. It's an induced magnetic field from the way it's travelling through space, through the interaction of the ions in the plasma and the sun's rays. So you get this sort of magnetosphere, but it's an induced magnetosphere. It's not indigenous to the comet. Okay, so what was more interesting was when they were looking, actually doing some radio data, ranging data to look to see how the two lobes fit together, to see if they could tell if that had affected the magnetic field. And what they found was that the lobes had got twisted. They'd obviously been one body which had separated and then come together again, twisted. But other than that, I'm afraid I can't tell you much about the magnetic field.
You gave us a good insight on the various compounds, but were there any heavy elements like trans-uranium elements or something like that?
I don't know. I only know the composition of the dust was iron magnesium silicate on the basis of the spectrometer. So the composition was done by UV vis spectrometer, and I'm not sure how good they are on. You know, they're not giving you a chemical composition. They're giving you a mineralogical composition. They're telling you, you know, what molecules you've got there, not necessarily what elements. So I don't know the answer to that. But given that it's made of, you know, primordial dust, there should be elements there. But it's not radioactive. All right. It's not radioactive.
Thank you, Professor.
You were talking about the nomenclature of the mission Rosetta 5D, the history. I was wondering about how the nomenclature of comets is done. So how did that name 67P?
Okay, so it's a short period comet. So this one comes in, it's actually, its orbital period is about 6.5 years. So that's what the P stands for. 67, well, it was number 67 that had been
Serial
spotted.
Number?
All right,
Okay.
and so when it was spotted by Dr. Churyumov and Dr. Gerasimenko, all right, so comets are named after the people who find them, unlike asteroids that aren't. However, there have now so many comets been found since 67P was first found that actually they've they've now got a different way of naming them, and it's named. Oh, it's horrendous. I can't remember how they name them, but it involves the year that it was on. It was found, so it will be 2018. All right, if it was found today, and then there's 2 letters which designate which 2 months of the year it was found in. All right, and so where are we? February. So this would be A, because it's February, naturally, January and February, and then it might be another letter, Z, because it was found in the last week of February, or W, because it was found in the second week in February. You know, it's complicated. And then, not finished, and then there's some letters at the end which signify which observatory the observation was made. So here it would be JNP, presumably. Okay. So, you know, it's complicated.
Where does Rosetta's findings stand in our understanding of the delivery of molecules essential for life? I mean, does it add anything, or is it just...
We know now that there are very complex molecules there. I mean, there's a bigger range of molecules. There's a really big range of nitrogen-containing molecules.
Glycine is
glycine was one of them, but there's a whole range of other ones. Very little sulfur was actually found, sulfur-containing. So that group of organic molecules with sulfur in. So there was sulfur dioxide and hydrogen sulfide and all that found in the gas by Rosina, but neither COSAC, which was analogous, a German instrument similar to Ian's instrument, neither COSAC nor Ptolemy detected very much in the way of sulfur-containing molecules. There was much more noble gases there than people thought, which is really interesting. And then the real humdinger that Rosina detected was they found oxygen, which was just not expected at all. And it's like, well, hang on a minute, there should not be any free oxygen hanging around at that time in the protoplanetary disk. It should not have been there. And so all the thinking is that actually perhaps you've got oxygen gas that had been trapped within ice and that was released. And so that was really interesting, because as we know, oxygen is, you know, thought to be essential for life, and it's also thought to be, if you've got oxygen somewhere, you can have life, perhaps, certainly on the Earth. And you know, you've got worries about disequilibrium with other species there. But they found oxygen on this comet as a building block, as something that's there which shouldn't be there. So that was one of the more interesting discoveries. So.
Thank you.
Okay, thank you. Thank you. Thank you.